OpenAI spends over $700,000 per day running inference on ChatGPT. That's not training costs. That's just serving responses. Meanwhile, a 70 billion parameter model on a single GPU crawls at 8 tokens per second. Users expect 50 or more for a smooth experience. The gap between 8 tokens per second and 50 is just good engineering. This video covers the techniques that bridge that gap. Every optimization starts with the KV cache, so let's understand it first. In a transformer, each attention layer computes key, query, and value vectors for every token. During autoregressive decoding, the keys and values from all prior tokens are needed for the current step. Without caching, you'd recompute them each time, a quadratic operation that grows expensive fast. So the model stores these vectors in a cache. That's the KV cache. It grows linearly with every new token generated. For Llama 3.170b with 32,000 token context, the cache balloons to 80 gigabytes. The model weights themselves are about 140 gigabytes at 16-bit precision. The cache alone is bigger than most GPU memories. This makes the KV cache the central bottleneck in inference. It limits how many requests you can batch together. It constrains how long context can be. And it forces memory management to be a first-class concern. Every technique we're about to discuss tackles this problem from a different angle. The first major breakthrough is PagedAttention, introduced by researchers at UC Berkeley in 2023. In standard inference engines, each request's KV cache is allocated as one big contiguous block of GPU memory. The engine guesses the worst-case sequence length and reserves that much space. The problem shows up immediately. Most requests are short, maybe a few hundred tokens. But memory is reserved for thousands. Studies show utilization as low as 20 to 40%. The rest is wasted. PagedAttention fixes this by treating the KV cache like virtual memory in an operating system. The cache is split into fixed-size blocks of 16 tokens each. Blocks are allocated on demand as tokens are generated. They can be stored anywhere in GPU memory, non-contiguously. A block table maps logical positions to physical addresses, just like a page table. This eliminates fragmentation entirely. And for beam search, the benefit doubles. Multiple candidate sequences share the same prefix blocks using copy-on-write. This is exactly how operating systems handle forked processes. Memory savings can reach 55%. The second breakthrough is continuous batching. Traditional inference engines use static batching. They collect requests until the batch is full, run them all together through the model, and wait for every single one to finish before starting the next batch. Here's the problem. Imagine a batch with a short query, what is Python? And a long code generation task. The short one finishes in 5 tokens. The long one runs for 2,000. With static batching, the short request sits idle for the remaining 1,995 steps, wasting its GPU slot. The GPU is underutilized. Continuous batching changes the game. After every single decoding step, the engine checks which requests are done and removes them immediately. New waiting requests are added to the batch. The batch reshapes every iteration. Short requests finish fast and leave. Long requests keep running uninterrupted. This was formalized in the Orca paper from 2022, which showed 3 to 5 times throughput improvement over static batching. Every modern serving framework uses this approach. It's the single biggest throughput multiplier in the stack. The third fix is quantization. Model weights are stored in 16-bit floating point by default, that's FP16. But you don't need all that precision for inference. The key insight is that neural networks are surprisingly robust to reduced numerical precision. 3 major quantization schemes emerged. GPTQ uses second-order information to find which weight values matter most. AWQ, activation-aware quantization, observes that roughly 1% of weights correspond to large activation values. It keeps those at higher precision and compresses everything else. GGUF is the format used by llama.cpp, offering multiple bit-level options with importance-weighted precision. The results are dramatic. A 70 billion parameter model at FP16 needs 140 gigabytes, requiring 2 to 4 GPUs. At 4-bit precision, it drops to just 35 gigabytes. That fits on a single RTX 6000 or a dual 4090 setup. The perplexity loss is typically under 1%. For most applications, the quality difference is invisible. On H100 hardware, FP8 offers another path, native 8-bit support through dedicated tensor cores. This nearly doubles throughput compared to FP16 without accuracy loss for most models. The fourth fix addresses a fundamental limitation. Autoregressive generation is inherently serial. You cannot compute token 5 until you have token 4. Each step requires a full forward pass through the model. This is a hard sequential bottleneck. Speculative decoding breaks it. Here's how it works. A small draft model, say 7 billion parameters, generates several candidate tokens very cheaply in sequence. Then the large target model processes all candidates in a single parallel forward pass. It accepts the tokens that match its own distribution and rejects the rest using a rejection sampling scheme. Because the target model's forward pass costs roughly the same regardless of input length within batch limits, verifying 4 or 5 tokens costs about the same as verifying 1. Typical speedups are 2 to 3 times. Here's the critical detail: the output distribution is mathematically guaranteed to match the original model exactly. There is zero quality loss. This is a pure systems optimization, not an approximation. Sometimes a model simply cannot fit on one GPU. Llama 3.1405b requires roughly 800 GB of memory at 16-bit precision. That's 10 H100 GPUs just to hold the weights, with zero room for computation or cache. Model parallelism solves this. There are two main strategies. Tensor parallelism splits each individual layer's matrix operations across multiple GPUs. All GPUs work on the same layer simultaneously, then synchronize results. Pipeline parallelism splits the layers themselves. GPU 1 handles layers 1 through 20, GPU 2 handles 21 through 40, and so on, like an assembly line. In practice, production deployments use both. A 405b model might use tensor parallelism of 8 across GPUs within a node, and pipeline parallelism across multiple nodes. The key requirement is fast interconnect. NVIDIA's NVLink at 900 GB per second makes the synchronization overhead worthwhile. These techniques don't exist in isolation. They're combined inside serving frameworks, the software that actually deploys models into production. vLLM was the first to package PagedAttention with continuous batching and prefix caching. It's open source under Apache 2.0 and has over 43,000 GitHub stars. It handles most production workloads out of the box. Together.ai runs it across thousands of H100s, serving millions of tokens per second. TensorRT-LLM is NVIDIA's offering. It adds a model compilation step that optimizes CUDA kernels, fuses operations, and auto-tunes for specific hardware. It supports INT4, INT8, and FP8 quantization natively. On H100 hardware, TensorRT-LLM is generally the fastest option, roughly 1.8 times faster than vLLM for the same workload. The trade-off is complexity. Model compilation takes 30 minutes to 2 hours per configuration. Both frameworks now support speculative decoding, quantization, and multi-GPU parallelism. Choosing between them depends on your hardware and tolerance for setup time. LLM inference optimization is a systems engineering challenge with enormous payoff. The KV cache bottleneck, PagedAttention, continuous batching, quantization, speculative decoding, and model parallelism, each technique solves one piece of the puzzle. Combined, They turn a 70 billion parameter model from a slideshow at 8 tokens per second into a real-time experience at 50 plus. The gap isn't magic. It's just good engineering applied to the right bottlenecks. If you found this useful, like and subscribe. More deep dives on the way.